Hi folks, see you speaking again. In order to clarify our subject of today, which is the fan out, I actually chose to clarify two subjects at the same time, the fan out and the simplest possible counter, which is made of a couple of JK flip-flop circuits. Let's find out. So here we put the power on, here is the reset button, and here is the button giving pulses to the counter. The counter, if I'm putting it here for a couple of seconds, we have four big LEDs here, and here on the right side is the least significant figure. So when I press it, it's going to start counting, following exactly the table here. So 0001, it's exactly the one in our decimal. Then it's 10, 10, which is 2. Then it's 11, which is 3. So it follows 100, 100, 101, 110, 111, 1000, and then 9, the equivalent of 10, 11, 12, 13, 14, 15. And if I press one more time, it goes back to 0. So it doesn't matter where it is, okay? I can always press the reset. So it's bringing it back to 0, okay? So this is the simplest possible counter. Of course, you can replicate it anytime you want. You only need 3 packages, 3 integrated circuits. The 7476, it contains 2 JK flip-flops inside. So you use 2 such packages, so you can have a total of 4 JK flip-flops. Remember, 1 JK flip-flop can only store 1 bit inside. So you have access to 1, 2, 3, 4 bit numbers. And you have a reset button. You have a pulse generator. It generates pulses manually. So you need 3 integrated circuits, 2 push buttons, 6 LEDs, 4 here to show you the number, 1 for the reset, and 1 monitoring the pulses. Take a look when I press it. The light goes down. So this is a falling edge pulse you need, okay? Similarly for the reset, because this kind of JK flip-flops, they are triggered on the falling edge. Remember, the pedals are staying up, so either of them you press, you are going to get a signal, okay? Good. So this is our basic circuit. Let's find out the principle of operation for this one, okay? I'm going to pick up here a sketch. I prepared practically an empty one. You have 1, 2, 3, 4 JK flip-flops, and unlike the standard way we judge the diagrams from left to right, this time we're going to draw this, actually we're going to follow the signal from right to left, because A, the bit A, is representing the least significant bit, and that's exactly like here, least significant A, B, C, D, okay? So this is why we're going to follow from here, from right to the left, in order of the importance of each figure inside, okay? So now, there are no pin numbers yet. We're going to put them later. But right now, we identify the JK flip-flops. It has the 2 inputs J and K, the clock input or timing, set and reset. Remember also, for the set, for instance, the reason the signal is a falling edge is because you have a bubble here. Same for the reset. So what do? We want to disable the set. We don't want to use it. So I'm going to simply draw here a line, joining all the set inputs, and this is going to go to the plus 5 volt line. At the same time, remember also that the JK flip-flop, we are going to base the functioning of our little counter on the toggling state of the JK flip-flop. So how can you get the toggle? If you put both J and K active and you give pulses on the clock input. So for the J, it's very easy. You link it to the positive line right here, to the positive line, to the positive line, like that, okay? You do similar for the K. Anytime you see such an arrow here, This arrow means it goes to the positive line, +5, +5, +5, +5, okay? At the same time, I want the reset to be controlled. So I'm going to draw another line here where I link the resets. All the resets, they come together like this. So I'm gonna say here, falling edge reset signal, okay? And then, what do we do with the clock? I have here another one, a clock generator, like this. And then I'm going to connect it to the clock signal of the first JK. What happens then is anytime I press the clock, this output here, the normal output, I monitor with an LED. Standard values here are 150 ohm, by the way. 150 ohm, 150 ohm, 150 ohm. So anytime I'm going to press the signal on the clock, the output, the normal output, in the normal output we see what happens inside the flip-flop is gonna toggle. Exactly like this, okay? So if I'm only resetting everything and I take a look at one LED only, it's 0, now it becomes 1, then go back to 0, 1, 0, it toggles, you see? It toggles all the time, okay? So, the output toggles. How am I gonna get the next one to operate? I'm going to simply link from here the normal output right here to the next clock. So if I do this, it's exactly this wire here. From the output, it goes to the clock of the next JK, which is in the same package, okay? So now, if I watch both of them, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Because if you only use 2 of them, that's the only thing you can get, okay? If I disconnect that signal from here, like this, okay? Then I get only 0, 1, 0, 1, 0, 1 because only the first JK is connected, but the second one does not receive a signal from the normal output. So I connect it back over here, so I get again from 0, 0, 1, 1, 0, 1, 1, and so on. So then I'm going to do the same, cascading from the next normal output. I'm going to give a signal to the next clock, and then from the normal output of the next. See, it's a very easy way to connect all the 4 of them. So this is why now, when I'm following, they just go through all the 15 positions, okay? And they restart from 0, okay? So here is the point. If I'm just putting some pin numbers, this is one package here, because it contains 2 JK flip-flops. It's called 74LS76. And I have another one here, 74LS76. Okay? A very important note about this package is that the ground of the package is on the pin 7, is not on the pin 7 or 8 as we expect, is the pin 13. And the VCC is the pin 5. So very important because there's not a standard package like the ones you know, okay? Anyway, now if I put some pin numbers, like 4, 16, here is 9 and 12. These are the JKs of the 2 flip-flops. Then the clock is the pin 1 here and the pin 6 here. And the normal outputs, this is the 15, this is 14, this is 11, and this is 10, okay? And it's going to be the same on the next package, okay? So don't worry, I'm gonna give you a much nicer drawing you're gonna find out to download from the Google Drive. But just to establish the principle of operation, once I did these links, everything is gonna work fine. However, depending on the packages you may have, sometimes you are going to notice that the counter does not advance from the first JK to the second or from the second to the third and so on. Why is this? You take a look here in this node, okay? it doesn't matter what is the direction of the flow regarding this output here. Let's just suppose the direction was like this, okay, out of the output. What happens according to the second Kirchhoff's law is that the sum of the currents entering a node equals the sum of the currents exiting the node. So this is the only current entering the node is going to be distributed in two directions, one here and one here. In other words, from the output here, I'm going to monitor using the LED. And here, if you take a look at this value and you want to know approximately what is the current through the LED, remember that the voltage across LED is approximately 2 volts. If the LED is one of the standard colors, which are red, yellow, amber, green, okay? And then, if the voltage at the output was approximately 4.5, you're going to find the voltage across the resistor approximately 2.5 volts. Why? Because 4.5 minus 2 volts across the LED is 2.5. With the 2.5 volts and 150 ohms, you're going to get approximately the current through the LED, approximately somewhere around 16 milliamps. Okay? Now, what happens is the maximum amperage coming out of this output here for a standard package 7476, one output generates at maximum, in the best possible scenario, no more than 16 milliamps. How do I know that? It's from the specifications of the manufacturer. And if it is 74LS76, it may be about 3.2 milliamps. Remember the letter L from here, LS, the letter L from here says low power. So if it absorbs low power, this is why the output amperage is a bit lower. Why the amperage? Because for both packages, the voltage is the same, it's 5 volts. So what can be lower, the power being made of both voltage times amperage? Lower is going to be the amperage, okay? So what is the problem? The problem is the current here is distributed in two directions, to the LED and to that input, which is the clock. And here, for the input from the same specifications of the manufacturer for a standard package 76, the maximum current absorbed by an input, so this time is the worst case scenario, okay, is one input absorbs up to 1.6 milliamps. So this is why sometimes the next JK may not operate properly, because 16 milliamps from here plus 1.6 milliamps from here goes anyway over 16 milliamps, which is the maximum allowed by that output. And then you need to do something to correct that problem, okay? And here is actually the definition of what they call the fan out. If you wouldn't have the LED, but you were distributing the current from that output to not only to one input, but to several inputs, if you do a simple calculation here, like the ratio between the output current versus the input current, best case scenario for the output, which is the maximum amperage, 16 milliamps, over the worst case scenario for the input, which is 1.6 milliamps, it gives you 10. This ratio between the output current versus the input current is simply called the fan out. What does it say? It says how many inputs can you draw from the maximum current distributed by one output only. In our situation, for a standard 7476 is 10. So the fan out for a original series 7476, the fan out is 10. And this is important, especially when you combine different kind of packages, different technologies, because not all of them they have the same fan out. For instance, the CMOS, they have between 50 and 100 the fan out, but if you only have CMOS gates or integrated circuits, when you combine them with the TTL, you have to be very careful, because you have to take a look in the specs of the manufacturer to fix the thing with the fan out. Now, in our situation here, how can we fix that little problem? Okay, how can we make all this operating? First case scenario, you are lucky. I arranged well my integrated circuits, everything is just working fine in that simplest possible diagram. But what if the simplest diagram doesn't work? Take a look, one option you have. One option is to higher the value of that resistor here, because if you do, remember the resistor in series with the LED, like with any diode, is a current limiter, so it limits the amperage inside. You increase the value of that resistor, you reduce or you diminish the current through the LED. So by reducing the current through the LED, you put the output in a better position. But by reducing the current here, increasing the resistor, you reduce the brightness. So sometimes you may need a higher brightness. A second solution is you leave the resistor in place, or even if you higher it, you look for an LED, the new generation of the LEDs, which are extremely bright for very low amperage. So that may be another solution. But there is another situation, is if you take a look here, the complementary output is the opposite of the normal output. So what if you connect here between the complementary output and the next clock input an inverter? Because this is already opposite to that one here. Complementary is opposite to the normal output. It's like you have an inverter connected. By using a second inverter here, what you receive here at the clock input is exactly what this one delivers. And by doing this, guess what? You can only use the normal output to drive the LED, and use the complementary output, which is another transistor inside the package, to drive the clock. And this is another way to solve that problem related to the fan out. Okay? So I'm going to show this to you over here. So it's exactly where the diagram shows the orange node right here, the current coming from the output distributed in the two directions. Okay, and that's how you realize if your diagram doesn't work fine, you have to do something. Okay, and this is exactly the most elegant solution if you want. Instead of having here the signal coming directly to the input of the next JK, you only reserve this normal output for the LED, and from the complementary output you connect an inverter to the next clock input, and you do this the same. So you may say, hey, but in that situation you need a new package. Not necessarily, because you use the same package actually already for the actual push button generating the signal, because this is the pulse generator, this is a debouncing circuit for the push button. The reset does not need a debouncer, because during 20-30 milliseconds, if you give a signal for the reset and it's bouncing inside the switch, it doesn't matter, it simply resets. Here, by the way, is the note about the power supply. This is a standard package, ground on the pin 7, VCC on pin 14. That's not a standard, ground on pin 13, VCC on pin 5. So you already use here two inverters from the package. Remember, any standard, the most of the standard packages for inverters, they contain inside 6 inverters in the same package. So you have 2 here, and you only have to add 1, 2, 3 over here. So you still have the same package already in use, so you don't need to add another package. And this is how you solve the problem, okay? Now, another thing that can be stated right now is that if I take this diagram here counting up, or this one counting up, how can I make the simple counter? That's a very rudimentary counter actually, and the main purpose of it was to be actually used to clarify the fan out. How can I make it counting down instead of counting up? It's simply by, without using the inverter as you see here, you simply take the complementary output to drive the next clock input, the complementary output to drive the next clock input, and so on. And this way, take a look what happens. I'm doing it right now. I got the power. So I pick up the wire from the normal output and I connect it on the complementary output, which is adjacent to it. Instead of pin 11, I have the pin 10. Now I pick up the wire from the pin 15, I put it on the pin 14, which is the complementary, okay? And I do the same for the next package, pin 11, I put it on the pin 10, okay? So when I put the power back on, right now, okay, I reset. It doesn't matter what it was showing before, I reset. And if I press it one more time, just one time, it's gonna go to 15. So remember, when it is 15, and I press the button one more time, it goes to 1110, which is 14. Then 1101, which is 13. 1100, 12, 11. Now 10, 9, 8, 1000, 7, 6, 5, 4, 3, 2, 1, and 0. And of course, if I reset, it's already reset, I press it one more time, it goes back to 15. So it counts down. So how can it count down? Simply because by doing this, you connect the complementary output directly to the clock input of the next, so you don't have the inverter anymore. So with this kind of diagram counting down, you don't have any problem with the fan out, because the normal output monitors only the LED, and the complementary output is used to energize or to drive the clock input of the next package, okay? Now, the next legitimate question you may have. Okay, I have a counter here in binary. Everything is just fine. How can you get my numbers on a display? And that's exactly the subject we're gonna get next time. How to convert these binary numbers, which are only 0, 1, 1, 0, whatever, how to convert these numbers into decimal. So we're going to discuss next time about decoders. Thank you very much for today. Bye-bye.